Section 3.11 Polyatomic Molecules. So first, let's look at this SF6 molecule with a OH point group. And then all 6 fluorine atoms can be assigned into this asymmetry, E symmetry, and T1 symmetry. This is AG, this is EG, this is T1U. So this AG symmetry is completely symmetric with respect to all symmetry operations. So basically it's just all 6 fluorines in the same phase. It may interact with the 3s orbital of sulfur. This is T1U. U means anti-symmetric with respect to the inversion center. It may interact with the T1U orbitals of sulfur. That's the 3p orbitals. So this T1U interact with T1U. So and then we have a this E symmetry. I think this is EG symmetry. It can actually interact with the 3d z squared and 3d x squared minus y squared orbitals of sulfur. However, because the difference between this MO energy and the atomic orbital energy of sulfur is very large, the interaction is small, so this 4 electrons are weakly bonding electrons. All right, and then in total we have a total of 8 bonding electrons, and then plus 4 weakly bonding electrons, a total of 12 bonding electrons. That means we have a total of 6 bonds. For more detail, you should watch this video on octahedral point group. This video analyzes the symmetry of molecular orbitals. And then this one is for ammonia, for tetrahedral, and D4H point group. This is ammonia. This is ammonia with a C3V point group. And in a C3V point group, it's possible to assign the 3 hydrogen atoms or the 3 1s orbitals to these symmetries, asymmetry and E symmetry. This asymmetry interact with this 2s orbital of nitrogen because this one also has a asymmetry. And this E symmetry will interact with the asymmetry of this 2 of the p orbitals, 2px and 2py will interact with this E symmetry. And also there's a 2pz orbital. This 2pz orbital in ammonia on this nitrogen atom has a asymmetry, symmetric. It's symmetric with respect to rotation and reflections. So this 2pz also interact with this asymmetry. So asymmetry here, and among these 3p orbitals, one is asymmetry. So the 2pz, 2s, and A interact with each other. All right, and then you get A1, and A1. These 3 are asymmetry from this orbital, and from the 2pz orbital. And then you have E symmetry, 2 of them, and E symmetry, 2 of them. You form the degenerate bonding orbital here, 2 of them, and 2 of them virtual empty anti-bonding orbitals here. And then finally you put valence electrons into those orbitals. All right, you have a total of 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. 6 of them are bonding electrons, so you have 3 bonds. And this is considered non-bonding electrons. So this may be considered as the lone pair electrons on nitrogen. So this is actually a mixture of the s electron and 2pz electron of nitrogen. Now those are the shapes of those MOs. So again, this is just the 2s orbital of nitrogen in the middle, and then the 1s orbitals. All right, over here it's the 2pz orbital. Oh, I'm sorry. Where's that? 2pz orbital can also interact with this A. Okay, it's over here. I think it's over here. And then those are the degenerate orbitals of this from this hydrogen atoms and from px and py. So let's say this is py and then this is px. All right, so again, we have 6 bonding electrons, and this is non-bonding electrons, mostly from the 2pz. But I want to say this 2pz can interact with the 1s orbitals of hydrogen atoms just slightly, okay, slightly. So this is not 100% lone pair. It contains a little bit sigma bonding character. Now, what's the relationship between symmetry adapted MOs versus those localized MOs without symmetry? So on the left-hand side, you're looking at water. You can have like A1 symmetry. Just imagine this is oxygen, hydrogen, hydrogen. And this is A1 symmetry, this is B2 symmetry. And actually, if you do a linear combination of A1 and B2, you can create, okay, this is just this OH bond and this is this OH bond. So really, localized MOs in water are linear combinations of the symmetry adapted delocalized MOs. And vice versa. Actually, if you do a linear combination of these two, so for example, this one minus this one, you'll get this B2. This one plus this one, you'll get A1. So in the end, symmetry adapted delocalized MOs, so these two, are linear combinations of localized MO. And localized MOs are linear combinations of symmetry adapted delocalized MOs. Finally, an interesting example, this is B2H6, 2 borons, and we have 6 hydrogen atoms. This is interesting is because this hydrogen bridge is bonded to both boron atoms, and that's why this bond distance is longer than this one. So this is a weaker bond than a typical boron-hydrogen bond. So if we look at the MO of this molecule, they have this bridging hydrogen atom, just one of the 2 bridging atoms, have constructive interference with both boron atoms, all right, with both borons. And there's 0 nodal surface, okay? And over here, 1 node, over here, 2 nodes. So again, those are symmetry adapted MOs, and you can see this hydrogen can be bonded to these 2 borons simultaneously. And these are called symmetry adapted delocalized MO. That can be used to explain the phenomena of those hydrogen bridges.